All right. Hello, my name is Raul Sanchez.
And my name is Jeanette Hernandez.
For our project, we decided to use an ultrasonic sound sensor and its applications through how it can be used in like backup detection. The equipment we just use the 82, P-Spice, the program, breadboard jumpers, and then the sensors, a microcontroller, and some LEDs. I have LCD as optional because it's not really used for anything more just to so that I can see it and just another way to confirm data and compare. This is the module itself, like a short schematic of how it works. It sends in pulse to trigger, and that pulse has to be constant. You can set it using a clock or making a pattern through the pattern generator in the 82. Once you have that constant trigger, it will activate the module to send 840 kilohertz pulses, and then those pulses they'll travel out, and then based on the distance, it will give you the time taken shown right here, and then that's through the echo pin. So the goal for this is we want to showcase how the sensor can be used for a lot of different reasons, a lot of different applications through kind of backup detection or for other systems, maybe large equipment. I know cars use this a lot. I think 2005, 2006, newer have some sort of backup detection. Tells how close or far someone is from an object or an obstacle before, so they don't get into an accident.
All right, so to achieve our goal, we first made a piece-by simulation of the frequency wave the sensor uses to detect objects. This works similar to how bats or dolphins use a certain frequency to get a better picture of their surroundings. We used a microcontroller to set the trigger to activate the sensor, then used other pins on the controller to have the LEDs trigger when an object surpassed a certain threshold we set.
So down here, this is our P-Spice simulation. This one we looked at through someone's research using a rangefinder, and this is a simulation of the 40 kilohertz wave and how crystal in the one side of the module sends out, it creates a frequency. And it has to be, this one is just set to be 40 kilohertz, and I think all or most ultrasonic sensors are around the same. And this is just a simulation of it. And as we can see through the simulation is that it kind of peaks at 40 kilohertz, which is exactly where we want it. And then this is the breadboard. It's really simple. It's just a sensor. It has its trigger and the echo. The echo is what we look at, and that's where the channel one would also go for the 82. So that because we want to read what's coming out of it, not what's going into it. That's why we don't put it on the trigger side, but on the echo side. And then the LEDs are just there, standard with a resistor before them. Green is furthest away, and then as it gets closer to red, you'll see them light up when something gets too close. And then the microcontroller. The microcontroller, that just kind of pushes out, is there so that we could use it to kind of set points. You can do this without using a microcontroller and a counter, but I think it's a little easier to just use the controller. Here's the code. A lot of this code on the side is mostly on this side is mostly for the LCD, which isn't really needed. The only ones that are needed would be these pin modes to kind of tell the microcontroller to turn on LEDs in whatever order you want. And then we also have right here a conversion formula for the data that we get. And here is what these were set at before, 17 centimeters for the closest it would turn on. And then we just used a bunch of if-else statements to kind of set the points where we want them to light up. And here is the data we can get from the 82 in numerical form. The only problem is that with the microcontroller is that this reads it accurately, but I feel it's not as consistent as the 82, and it's a bit more, as you can see, with these inconsistencies. And now I will show the circuit itself. Now here on the circuit, we can see that when I put this here at around 30 centimeters, the green light will turn on. The closer I get, there's the yellow one at around 17 centimeters. And if we get closer, there. The second red one will turn on around 9, and that's at around 5 centimeters is when it's too close and all LEDs turn on. And it works. The further something goes, it'll go down until it's not. Then we get closer, and again, you'll see them light up in order, and that's through the microcontroller setting up the pins. We'll share the waveform, and you can see it work with the actual circuit.
Yeah, so with the rising part of the square graph is when the microcontroller sends the signal out to the object, and then there's that little wait time in between, and then when it drops, that's when the object, or when the component receives back the sound wave from the object. So the closer it gets, the smaller or the thinner that square wave gets. And then conversely, if it's far away, the square wave will get wider. So it takes longer for the waves to bounce back and forth.
And then here we just have one of the waves where it's set at around 17. On the x-axis, you can look at the time, and then through there you can use the conversion formula that's given to change that into centimeters. And through having physical measurements and other types of measurements, you can kind of double check your data and see where the error is. Here is another one. This one's closer at around 8.5. And then this is kind of as close as it can go through before it starts acting weird. The sensor itself kind of stops working at around closer to than 3 centimeters, since it doesn't have a good enough angle to kind of properly receive it unless you had something that was curved, because something that was flat, it has a hard time picking up the signal when it's too close. You can remove that non-operational area by just setting your 0 3 centimeters higher, and then you'd have a lot more accurate data.
So these are the hand calculations to get the distance from the waveforms. So for example, like I chose the 0.5 milliseconds that was found on the x-axis of the waveform, and using the constant that is the velocity sound and dividing it by 200 milliseconds, we get 8.5 centimeters. So theoretically, at this time, we should get that distance. And then I chose another, which is just 1 millisecond. And using the equation, I got 17 centimeters.
Yeah, these were the examples from the ones from the waveform screenshots that we had. If you just take that milliseconds, put them in, you can get these answers. That's where we got them from. And just kind of to end it off, there's our reference for the PSpice simulation that we had up top. Thank you.